Okay. There is a growing interest in studying the functional response to different groups or treatments, also in determining the correlations between the groups in biomedical studies, but also in many other fields. Traditional approaches in general assume independence between groups. In this work, we analyze a new covariant function for Gaussian processes, which is defined in a non-separable mixed domain of continuous and categorical variables that models the covariances between observations that belong to the same group but also to different groups. This new model or new kernel was proposed recently by Lee, Bernaghi, and colleagues in their work called multi-group Gaussian processes. But this original work do not make inference on the similarity distances between groups for the general case of K groups. So our goal in this work is to specify and infer prior distributions for the similarity distances between groups that satisfies the axioms of a distance metric. Then we also compare among different approaches. Traditionally, Gaussian processes with group effects are based on the product kernel of continuous and categorical kernels, where the categorical kernel assigns covariance of 1 when the observations belong to the same group, and a covariance of equal to 0 when the observations belong to different groups. This kernel yields a covariance matrix that is block diagonal with 1s in the diagonal and 0s out of the diagonal. The result is independent GP functions across the groups. However, this traditional separable GP, although it is not commonly used or it has not been commonly seen in practice, it's easy to be extended to consider correlations between groups or covariances between groups, just to consider certain covariances between observations belonging to different groups in the categorical kernel. This kernel will be a valid kernel as long as the covariance matrix is positive semi-definite, and this will be if the covariances between the groups forms a valid correlation matrix. And this is straightforward in STAN, for example, or in probabilistic programming. However, in this work, we are especially interested in the multi-group covariant functions proposed by Lee et al., which extend the matter class of covariant functions to be defined in a non-separable mixed domain of continuous and categorical variables. We focus on the multi-group version of the square exponential kernel. In this new kernel, we see that the main new parameters are the similarity distances between the groups, that these similarity distances scales the length scale relatively between groups, and also the marginal variance. These similarity distances has to form a distance matrix, and this distance matrix has to be a valid distance matrix, so it has to fulfill the axioms of a distance matrix. So let's focus, or we should put the attention on the triangle inequality property in order to implement this approach properly and efficiently in probabilistic programming. In the sample where we feed a GP function for 3 different groups, using this multi-group kernel, we are able to estimate covariances between the observations belonging to different groups, which can be especially useful in unbalanced data sets where groups with fewer observations can get benefit borrowing information from the other groups through the correlations. It can be also useful to discover the similarities, the correlation between nonlinear functions using GPs. Has also drawbacks. Varying the length scale within groups is not straightforward. The covariance matrix is no longer positive definite, and it has slower simulation computation than the regular GP. Okay, how to specify prior distributions on a distance matrix, which is the main goal of this work. Then the first approach we implemented is specifying the prior distribution directly on the distances, but constraining some of these priors in order to fulfill the triangle inequality. So for example, with 4 groups, we have 6 different distances between pair of groups. So we can define independent priors for 3 of the distances, and for the other 3, we have to define constrained prior distributions in order to satisfy the triangle inequality. By analyzing all the combination of 3 elements of the distance matrix, it's easy to know which constraints we need. However, it's not an elegant or practical approach in terms of coding, because when the number of groups increases, you have to put a lot of constraints. So, and also Stan gives sampling warnings that the constraint has been slightly violated during sampling. The more groups, the more warnings. So the second approach we implemented is also specifying the prior distributions directly on the distances, but now using the mean plus matrix multiplication operator in order to guarantee that the distance matrix is a valid distance matrix. This mean plus matrix multiplication is closely related to the shortest path problem. So we can specify independent priors for all the distances and then apply this mean plus matrix multiplication over the distance, the sampled distance matrix, and we obtain a valid distance matrix. So this is a more efficient and elegant approach. And the approach 3, we don't specify the prior distributions directly on the distances. Instead, we do it indirectly through embedding the distances into a Euclidean space. We draw k vertices in the Euclidean space where the vertices can represent the groups, and then compute the Euclidean distances between the vertices, and this might represent similarity distances between the groups. So from experimentation, we evaluate the performance of the different approaches in terms of root mean square error and ELPD. We found that all the approaches that considers correlation between groups performs better than the traditional separable GP. The improvement is higher, is larger, as the true correlation between the groups is also larger, and also when the degree of unbalancing is also higher. On the other hand, when the true correlation between the groups is small, or the groups are equally sized, then the improvement is not so significant. When we look at the estimated between group correlations, okay, I forgot that. Maybe if we look which of the approaches performs better, maybe the multi-group kernel, when we specify prior distribution directly on distances, performs better than the other ones, slightly better. Also, we found that the multi-group kernel, when specifying the priors directly on the distances, also is able to estimate the correlations between groups better and more accurate and more close to the real ones than the other two approaches. We also make experiments in order to evaluate the benefit of inducing prior knowledge on the similarity distances. The benefit of defining informative priors. But in terms of predictive performance, we found that inducing prior knowledge or defining informative priors doesn't improve much the performance in all the settings we tested, but in the true correlations of the groups or the degree of unbalancing. The performance as a function of the amount of induced prior knowledge is mostly constant. So, however, if we look at the estimated correlation with this, in fact, or actually expected, the estimated correlations between groups are more accurate when we induce prior knowledge about these prior distributions. So that's it. Coding the constraints, the first approach, you say, I don't know, scale the groups. Defining more groups is maybe defining more than 5 groups or 10 groups, maybe the stand gives too much warnings. I don't know, I didn't test it. But I don't know, I think I tested 4 or 5 groups and it gives, if finally we finish, but I don't know, maybe it's not very confident.
I mean, the number of constraints grows quadratically, right?
Yeah.
So it's not going to look good.
I was just thinking about like some kind of LKJ style pie on this, which like makes it pretty, I don't know if that makes sense.
Yeah, it does actually. Yeah, because like the way the LKJ works is it's like a beta with certain parameters and everything, so there is a connection there between those.
So perhaps if we wouldn't start with a beta 1, 1 or something, but with something like partial correlations in some way, then we could have like more better constraints.
Yeah.
Okay.
Let's not see all the same hands here. No? Okay. So in terms of looking at the embedding in a Euclidean space, it seems like there's a lot of degrees of freedom there. So like how big do you make the vectors to do the embedding into? Like if I'm in n dimensions.
We sample the vertices. We sample the vertices through a multivariate normal.
No, but I mean how high dimensional? It can be you know, if we need to get a distance between 20 points, I can use 1, 2, 3, 1,000 dimensions in a normal.
Ah,
They all
okay.
yield
The
valid.
dimension is, in order to be more flexible, the dimension I think is k minus 1.
Okay.
K minus 1, you obtain all the flexibility.
Okay.
If not, if you define less dimension, then you are more constrained.
Mhm.
Yeah.
And have you looked at things other than like the L2 norm? Because once you have the vectors, you can use any of these distances, right? You can use L1 distance, L3, you can change them.
Yeah. Yeah. But
Could you also just say which one of the methods worked better? I couldn't tell from the color code in your plot. I think Hyunji's setting up, so I don't know if you want to go back, but just say which one worked better.
the mean plus multiplication probably works the better. But it's very close also. Also, this one, that is the separable GP, but considering correlations between groups, also performs better. But I don't know. I have the feeling that the multigroup kernel with the mean plus multiplication works a bit more